What's up, everybody? Welcome back. Today we are working on our barcode neural network training framework. What does that mean? So we are kind of on this like mega sidetrack where we wanted to use we wanted to make like a meal tracking app, and as part of that meal tracking app, I want to keep track of like the ingredients in my fridge. As part of that, I want to be able to scan ingredients as I place them, because then that will let me do things like, as I write down what I consumed, my website will know, hey, you have 2 liters of milk, which means you can make stuff that has milk. But if you had like 100 milliliters left of milk, I could, 1, tell you to go buy more milk, 2, limit your like things that you could choose to make right now into like a list of things that has the ingredients that you have, right? So that's kind of like, we ended up here. We started to do some like manual barcode processing. It's like kind of hard, right? There's a lot of like scenarios where this shit like kind of falls over. Just look at like this egg carton, right? It is hard for this egg carton to it's going to be hard to parse this, right? Because this egg carton is like really like messed up its barcode, and especially in like a patterned way where you're not going to have like one clean strip of horizontal data. So this is just one of like many examples, but something that can like creating some sort of like image processing that can turn this into something more scannable is what we want to do. We tried to do it by hand, we gave up, and now we're on making a neural network framework so that hopefully it can learn to do those things for us, right? And so we're kind of like in the first stages of this thing. It's kind of hard to see this right now, but this is like a barcode slapped on top of some random image. We have blue pixels indicating, what we said that the network should predict. Red pixels indicating that it like predicted that those pixels have the barcode, right? That's kind of what we're making right now. He like runs some convolutions and says at the end, hey, these are the pixels in your image that I think have a barcode in them. Great. That was kind of like the first easy step of this thing. I want to upgrade this today into predicting a bounding box for this thing. So like maybe instead of drawing like these pixels at low resolution saying these pixels contain the thing, I want to draw a box around the barcode. Is there one that like you can see a little better? It's kind of hard to see the barcode with all this blue and red shit on top of it, huh? I didn't consider that when I was looking at this earlier. But like maybe something that just draws a box around this thing, and then we can use that box to extract a high-res version of the barcode to do actual scanning, right? That's kind of like the workflow that this thing's gonna have. Is I point my camera at the thing, my camera sees a barcode in the middle. He says, "Oh, these pixels are the one that are relevant." Blow them up, do some scanning on the high-res version. That's like analogous to what we were doing by hand as well. And so why we have been doing so far is I googled like at some point, like object detection neural networks. I figured those are kind of like a good place to start and like kind of good inspiration. I kind of settled on using YOLO version 1 as our initial inspiration. It's kind of like there were kind of like a few types of networks, but YOLO was kind of like a good balance of like simple and fast, right? We eventually want to run this thing at 60 FPS on our phone, probably on CPU and WebAssembly in the browser. So something that works relatively quickly is good. And we're on version 1 because, we need to start somewhere. So starting with version 1 and working our way up into the future would be kind of nice. And so in here, one of the things that the YOLO network does is he draws boxes around stuff that he sees. Great. How does he do this? He takes his like initial big ass image, big being, 448 by 448, and he runs a bunch of like image filters, we can call them, over this thing. And at each level of image filter, he kind of like reduces the size of the image, with the idea being these filters that I'm running, are going to like extract high level features about this picture, right? You could imagine like edge detection is a really obvious one that you might do. In fact, we can actually see those if we look at them here. Boom, right? So like what we take like our input image, and you can see like sometimes he's going to doing some like edge detection probably here, some sort of like maybe different type of edge detection that's like saying blue is negative, red is positive. So he's doing something there. Here he's looking for, I don't know what, but you can see he's like doing some sort of like filtering to this thing and turning it into something, at each level, he does like more interesting. He uses the output of the last iteration to do more stuff, essentially, right? And so they kind of say, we're going to get more and more features at lower and lower resolution until we get to the end. and we just say we have a 7x7 thing, and we're going to just look at 7x7 by 1,000-ish, 1,024. Where this each in the pixel in the 7x7 grid represents like a region of the image, and then the 1,024 things is just like things that we know about those pixels, right? For each pixel, we have 1,000 things that we know about it. We just look at all of that shit and generate like some stuff, right? And the stuff that they generate is hand wavy. Each grid cell, so each of the like 49 pixels that they have at the end, produces many bounding boxes and confidence scores for those boxes. These confidence scores reflect how confident the model is the box contains an object. Is B here number of classes? I'm not sure. Formally, we define this as so they define like some sort of confidence value. We'll kind of skim over that for a second. What is the point of the string if it's going to depend on someone's external library to do the thing? We're not doing that. That's the whole point. That's the whole point. We're reading papers for inspiration. We're not even copying this paper directly. We're just using, we are looking at other network designs as inspiration for how we will design ours. So they do something like they define some sort of like confidence value per box, or yes, each box gets a confidence score. And so their confidence score is during training, they train it to say, if I have good overlap with the box that was the real box, then like that's a high confidence value. And then also if like this is supposed to be an object. So I guess like in some grid cells there will be no object, and so they kind of say you multiply like the probability that there's an object here by the probability that I think that this was good. And they probably use that for, I think they use that for like box squishing, right? So in this picture here, you see that there's like a ton of boxes being generated, but a lot of them are either like duplicates or not important, or like not good enough, right? So these confidence scores are probably a way of choosing which boxes they consider actually good. Well, technically he's using GLFW, and I'm curious to see if we can raise on GUI toolkit just in elsewhere. We actually are using our own GUI toolkit right now. It's already been done. Okay, so they predict confidence of boxes. They generate many boxes and they predict confidence for those boxes. For each bounding box, they predict XY width height of this thing and confidence. Great. The XY coordinates represent center of box relative to the bounds of the grid cell. The width and height are predicted relative to the whole image. Sure. Each grid cell also predicts C conditional class probabilities. These probabilities are conditioned on the grid cell containing the object. We only predict one set of probabilities per grid cell. Okay, so they are predicting like dog, cat, bike, right? That's what their thing is doing. That's not what we're doing, but that's what they're doing. And so they have class probabilities for like which, is it one set of class probabilities? Yes, so they predict many boxes. Then they say, which class do I think this box is? So they probably pick the best box out of that thing. Oh, at test time, we multiply the conditional class probabilities and individual box confidence predictions. So they say the prediction that this class exists, it's like we have, with test time, we multiply the class probabilities and individual box confidence. So they say, what is the probability that this object is of class dog? And what is the probability that that is an object at all? And what is the probability that we thought that this was a good prediction? Like that we made a box that is relatively correct. They kind of take all of those things together, which gives us class-specific confidence scores for each box. I see. So maybe like a dog and a cat are both very confident that it is, the dog and cat prediction are both very confident that they have a good box, and they're both very confident that it is a thing, but we're more confident that it's a cat than a dog. And so that's probably, so it looks like the box and the class prediction are like completely independent. And I believe that they at some point have to squish all these boxes out. I'm pretty sure that's like all this is for, right? So do they talk about this somewhere? I think I saw the word NMS in here. No. Suppression. Oh, yeah. Here we go. So where is this? This is in non-maximal suppression could be fixed to use as multiple detections. Oh, here we go. Inference. So just like in training, predicting detections on test image only requires one network evaluation. Grid enforces spatial diversity in the bounding box predictions. Sure, so you get diversity in boxes. Often it's clear which grid cell an object falls in, and the network only predicts one box for each object. However, some large objects or objects near the border of multiple cells can be well localized. Sure. So I think my understanding of all of this is that all of this like confidence score stuff is like related to the fact that they are predicting many boxes. So I think we just don't have to do that, right? I think that in our scenario, we're kind of like looking for 1 or 0 barcodes, probably. So I think that we can maybe a confidence score for, we'll have like some sort of confidence score for if we think there a barcode was found. Okay. Sure. So we need one thing that's like, is there a barcode in the picture at all? And then we predict a box, and maybe we do the same thing where we're like, do you think that you predicted a good box? That might be useful. Maybe we can kind of skip that part for now. Because we can probably hope that if it's very confident the thing is there, that we also predict a good box. Maybe. We might find out that like, maybe if there's like a lot of noise in the background of the image, it might learn that like if there's a lot of stripes that aren't the barcode, that it's like struggling to identify which part the barcode is, and that might be like useful signal in some way. So that might be like a useful idea to steal. But in terms of what they are actually trying to predict, they talk about it here somewhere. So they predict class probabilities and bounding box coordinates. They normalize the bounding box width and height by the image size so that we predict between 0 and 1. Sure, we can do that. That seems reasonable. I think that my understanding of these like neural networks is that like numbers closer to 0 are kind of better in general. So kind of trying to predict coordinates between 0 and 1, I think makes sense. They have X and Y coordinates relative to grid cell locations. If we're only trying to predict one barcode, I think we can get away with not doing that, right? Because they're doing this because there might be multiple objects in their scene. They might have like a dog, a cat, a bike, and a car. All of those things might be there, and so they want like to look at each area of the image and predict a thing. We don't really care about that. We only care about like one prediction at all. So I think that we can just parameterize relative to the center of the image or the top left corner or something. They used linear activation function for the final layer. Sure, that makes sense. We could get away with, yeah, sure. Linear activation seems reasonable. Optimize for sum squared error. Sure, so that's fine. We can do that too. We're already using sum squared error everywhere else. Chill. What else is going on here? It does not align with our goal of maximizing average precision. It weights localization error equal with classification error, which may not be ideal. We don't have that problem because we don't have classification error to deal with, probably. In every image, many grid cells do not contain an object. This pushes confidence scores those cells towards 0, often overpowering gradient from cells do not contain objects. Sure. So if most things don't have objects, then your overall training is going to like maybe trend towards just predicting 0 more often. So they fix that by kind of scaling their losses for other stuff. Sure. So they're like weight bounding box stuff 10 times higher than like if there's an object or not. Sure, that's reasonable. Sum squared error also, what the fuck did I just do? Sum squared error also, take that shit off. Go away. I don't want this. Go away. Thank you. Sum squared error also weights errors in large boxes and small boxes equally. Small deviations in large boxes matter less than small deviations in small boxes. That's true. So they predict the square root of the bounding box width and height instead of the width and height. Oh, interesting. Yeah, that makes sense. Yeah, so they say, because on a big thing, the error is less of a problem. So in that, like, sometimes you square stuff to make it so that large numbers have more impact, right? They get bigger fast. Numbers get bigger faster when you square. So like big numbers have more of an effect on like average. Here they're doing the opposite. They're saying that if the number is big, you want it to have less impact, because a big width, if you're off by 1 pixel, it's not as big of a fucking deal as if you're on a small box. So they predict the square root of the width and height. That's reasonable. They predict multiple bounding boxes per grid cell. At training time, we only want 1 bounding box predictor to be responsible for each object. So they pick 1. We don't do that. Probably. I think we can get away with only predicting 1 box everywhere. Probably. During training, okay, so here's kind of like the big shabam of what they're doing. So they're predicting, center. They're taking the squared error of the center, squared error of the square root of the width and height. Then they have like class score stuff that we don't care about. Although we should probably eventually look at the idea of showing it examples of barcodes that are images with no barcodes and doing something with that. I don't think, do they multiply? Oh yeah, so they go for each object here. So if there's no object, then that doesn't get contributed to loss. Sure. Okay, so what do? This is like intro/network arch planning. So we're going to do something like YOLO as inspo. Probably predict square root, width, and height. Predict barcode center. For now, we assume that there will always be 1 barcode, because that will kind of simplify experimentation of drawing the bounding boxes. And is that it? It's literally just like predict square root of width, height, predict center, and then use like mean squared error as loss target. So we just kind of like add up the squares of all of the incorrectnesses. Our network training will automatically figure out what to do there, and then we're chilling. We might want, maybe we have like their confidence score related to IOU intersect, like box overlap. So like if the network can learn that it predicts shit boxes sometimes, then we might want to like use that information to like not count that as a barcode or something. Alta4, thanks for the raid. What's up? Long time no see. Oh, we're working on this guy. Barcode isolator neural network from scratch. That's what we're working on. Mic muted? Certainly not. If I've been talking for 2 hours with the mic muted, like chat has like, they've got some responsibilities that they've got to cover. This image seems inappropriate. It kind of does, huh? Anyways, so like under this like red and blue shit, there's a barcode. We have blue as like the mask of the thing that we're supposed to be predicting. Red is like what we actually predicted. It's kind of doing its job. And we were just talking about how we're going to turn this into like boxes. So we're like, the goal for today is to draw a box around the barcode and use that for isolation instead of whatever the like predicting masks like we're doing right now. And we just went over a paper we're using as inspiration, YOLO V1, from like a long fucking time ago. I don't know if the date's in here at all, but it's old as fuck. And yeah, we've got a kind of idea of what we want to do. Okay, so plan of action is, let's start by like generating some boxes. We probably want to predict orientation as well, to be honest. They don't do rotated boxes in theirs, but I think we do want to do rotated boxes, because I think when we want to like actually start looking at the high res information of the barcodes, I think we want those to be aligned in some sort of like normalized space, that the left of the barcode's always on the left of the image type shit, and that the bar is always like semi-vertical. I think that will make everything else downstream kind of easier. So yeah, we'll probably do that. Have you watched the 3 Blue 1 Brown AI training course videos? Just wondering. I think I've like watched them at like 3.5 times speed once. Like a 1.5 years ago. So like retention was not very strong. But I know they were bangers. Okay, cool. Okay, so let's start doing stuff. So the first thing we gotta do is like generate box labels, visualize them, do some training, and then if that all goes smoothly, we can try to like generate some high-res images and try extracting. But I doubt we'll get here. I think this stuff will be kind of good for today. Okay. All right. Anyways, thank you again, Alta4 for the raid. I apologize for not acknowledging you that much, but my brain, I just really, focus. We gotta focus. I was at 0.8 because I'm Gen X. Yeah, I think watching 3 times at 3x speed is better than watching 1 time at 1x. I think watching 1 time at 3x is definitely worse than watching 1 time at 1x. Okay, so how does our image generation work? We have this like barcode generator thing that runs on GPU, and he does like a few steps as part of that. He like has a bunch of randomized parameters that he takes in, this stuff. And when he generates the barcodes, he like on GPU, per barcode that we're trying to generate, says, let me sample from those random parameters. And so presumably that's where this like width and height come from. Right? So when we have sample barcode parameters, he like exports the offset and scale of these guys. So scale is probably what determines width and height here, and offset is what determines the center. And rotation here. So we probably want these parameters exported somewhere. So we need these in like a buffer kind of like on their own that we can use to compare our final answers with at the end. Yeah. Okay, so, or just like visualize. We need to be able to pull those things off. Okay. So let's say that, how do we pull that stuff out? We have like instance mask. Where does like our we have like a mask somewhere. That comes from pass1 outputs. But we don't have to render the barcode to get the width and height out. So probably instance random parameters here. His job is to export bounding boxes when he samples these things. And so then he just says B boxes out here that gets B box bounding boxes here. And so we need to create this buffer that he's going to export into. So it's X, Y, width, height, rotation per barcode. So this needs to be 5 things, and this is going to be bounding boxes. Okay, cool. Which means that here we need to take that thing in. So this is going to be float star. Wait. Was it before? Where did we put it? Was it before or after? We put it after orientations. So this is going to be float star, B-box out. And I guess here we say B-box out. Global ID times 5 is going to be equal to X scale, Y scale, X offset, Y offset. What's a float 2? Just 2 floats next to each other. So I guess it's like something like this. Something like this? So what is this like X scale and Y scale? What like unit is this? It looks like it's in relative to the image width, which is kind of nice. Offsets are in pixel coordinates. Yeah, it does seem like these should probably be ratio image size, but whatever. So we could, do we have image width and image height here? We do. So we could convert these now for training labels. For now. Yeah, something like this. So these are already relative to width of image. these now have been converted to relative to width and height of image, we can probably assume that image width and height has they're square for now, so we'll just make that assumption for now and then regret it later. And I guess the first thing we should do is visualize this stuff, right? So I guess let's just make sure this like compiles in its current form. Here we have, what would we call it? Bounding boxes, probably. Yep. Okay, we need to like return this out somewhere though. So we have like instance random parameters. This gets called. And then we have bounding boxes here. Makes it out of here. Oh, which means that we have bounding boxes here. Okay. So what we should be able to do now is in like our image gen thing, we're kind of set up now to kind of draw the box on top. So let's figure out how to do that. So somewhere we call like make bars, and can we just like here, we need to like take bars for image we are visualizing. We need to copy them, copy from OpenCLand to CPU, copy from CPU to OpenGL. There's a way to like not do this, but this is just easier for us to handle for now. So this is like OpenCL is where we're doing all our compute. OpenGL is where we're doing like our GUI shit. So we kind of have to do this back and forth. And then render on top of image. This is kind of like the flow that we need to do. So we have like bars dot bounding boxes, and we should just be able to be like, let me look at the thing that I'm looking at. So, where do we know like which guy we're trying to look at? Dude, what are we doing? Whoa, what offset comes from self-selected image? So this is probably like we had some code here before we had the nicer index outer thing. But this is like our box slice. So this is the bounding box on OpenCLand. And we should be able to like copy this over. So I think it's like, we must have like math executor to slice to CPU deferred. Sounds kind of like the right thing. Box slice. We have some allocations to be doing. This thing is going to live on probably our like scratch allocator. Probably this is probably like a temporary thing. It's probably something like this. So we wait for this to complete because the transfer from GPU will take time. And then we have a thing that we can work with. So here we have on CPU 5 floats: X, Y, width, height, rotation. And we need to convert this, needs to be a buffer that we can render on GPU, probably with like render lines would be like a nice thing to call here. Which means that we need a buffer. We need a buffer that looks kind of like, if we have this point, this point, this point, this point, and we probably want to call render line loop, right? So we want a buffer that is like 2 F32s here, 2 F32s here, right? And then we'll call render line loop and it'll draw this box, probably. So we need to take the coordinates of each of the points in this box. Also, yeah. So X, Y is center, I hope. I hope it's center. I guess we'll find out very quickly. These are in right now normalized coordinates 0 to 1. We need them to go to OpenGL coordinates, which are -1 to 1. Which is fine. And then we need to extract corners. So how do you do that? We have, we probably want to convert theta to like an x and y axis, right? So if you have like, I don't know if this is clockwise or counterclockwise right now. We should probably figure that out. But so you have like angle theta, right? If you are like working with points in here, if you're like center and you want to find out this guy, you can kind of like take a multiplication of half the width by the x vector plus half the height by the y vec, right? And so like if we take this angle, like say this is this angle, I don't know if it's clockwise or counterclockwise, but say it's this, then we should be able to extract the x vector from this by doing cosine theta, and the y vector by taking sine theta. And then we should be able to like be like, I have this distance along that thing. Sorry, this is not quite right. How do you get this thing? So I have x vector. So if this is my new x, I want this and this, right? So this is s theta and this is cosine theta. Yeah, and then the y vector is just like the inversion of this. Cool. So I guess we want like, this should all go in like a fucking scope for now. Okay. So we want like x-axis is a vec2. I guess we want like sx is going to be sine theta, which is theta is res val 4. Okay. Cos theta, sine theta. And so our x-axis is cx sx. And our y-axis is... Hold on. I always have to draw this to figure it out. So if our x is cosine for x and sine x for y, this is negative sine x and cos x here. So it's negative sine x and cosine x for y. Okay. And so now what we should be able to do is we have like half width is res val 0, 1, 2 over 2. Half height is this. We have c center x. Fine. Cos x, sine x, and can we call this sine t and cos t? There we go, because now we can say that our center x is res val 0 and res val 1, except for the fact that these are normalized coordinates. We want them in OpenGL coordinates, which is funny, half width and half height actually become no divide by 2, because we'll say OpenGL space is 2x as wide. So we take half width in normalized space and double for OpenGL, LOL. This is minus 0.5 times 2, I think. I think this gets us into OpenGL space. So if center x was at 1 before, we subtract 0.5 and double it, and it's still 1. If center x was at 0, we become negative 0.5 and double it to negative 1. And that becomes negative 1 from 0. Yes, this is right. This is right. Okay. So now all I have to do is like construct our buffer. So GL buff is going to be something like... I don't remember. Probably this type of buffer here. So we have hold on, XYT program. Okay, so this guy is a bunch of V pauses. Okay, so we initialize this with scratch GL and like our data, right? So corners or something? So we need corners here. And this is going to be a array of bunch of these vertices? Yes. Okay. So we have center here. We probably want this as a vector. Okay. Okay. So X is, let's start top left, right? Top left is center plus half width times x-axis. Yeah, but minus. And center minus half height times y-axis. Okay, easy. And then we just need the four combos. So minus plus 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 minus. Yeah. Height. Those are our four corners, probably. Probably. I don't fucking know, man. We'll see. We'll fucking see. I don't know. Can we then be like render source is, you know, render source, initialize this thing, bind the data. So here we're like, figure out how to like use this buffer of shit with this program. So it's like solid color renderer program, use this and this GL buffer. Okay. What's this mad about? Shadows, fuck off. This goes into scope as well for now. Okay, and then what's he not like here? Box slice probably needs try. Okay. Half width and half height. These need to be vec2s as well. So we just kind of double them up. Boom, boom, boom. Now what are you pissed about? Cause center? No. Expected type F32 found. Oh. Right. This is like this. My bad. Center minus this. Yeah. 1, 2, 3, 4. So we have minus, 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 plus, 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 and plus, minus. Okay, there we go. This thing needs to be variable. And then we should be able to like just draw this shit. Render line loop with render source. And what we're talking here, transform is identity. I think it's like stud math transform identity inner. Okay, and then our color here. Can we just render this shit in blue or something? All right, what are the chances that this is right? I'm betting I'm on a solid like 20% that this is correct. Okay. It's not as bad as I thought it was going to be. It's definitely not great. But it's not that wrong either. Are we rotating the wrong way? Why are we so skinny? I have so many questions. We are drawing blue boxes. And hand wavy, their orientations, I think, are lining up. Like, I think, right, like, at least, like, the some of the lines are, like, the edges, like, this line and this line are parallel. Which indicates that, like, we're doing something right. Is it quartered? No, the size is totally fucking out of whack. Yeah, something here is very wrong. I don't know what, but something... Rotation seems right. Everything else just seems like totally fucked. Are the codes is our boxes always on the bottom left? It feels like we are not scaling our center position correctly. It feels to me like we're always in the bottom left. So what's going on here? So first of all, can we log what we got? Box at this. Let's just start here. I feel like that's the play. What is val? Okay, so here we got 3.9, 3. Okay, can we... Okay, so this guy... Oh, do we have width and height and offset inverted? Yeah, we did offset on the second half. My bad. So this is 0, 1, this is 2, 3, which means that we should just do XY width height. Like, what the fuck are we doing? In what world would anybody ever want width height XY? That's fucking crazy. That's crazy. Shouldn't you square that shit? Yeah, that's like a good point. There's like, that's a maybe. Okay, so now... Our center, we need to... Our center is like not being done correctly here. So wait, hold on. So we get... Here, we're getting box at X 1.8 or 0.18, 0.19. So that's over here. Y up is Y up. And so what are we trying to render here? Uh, 0 center. That's what it is. So we're relative to the center of the image, but in normalized space. I think. Oh, okay, wait. That's pretty good. That's definitely like, so that's close. The problem is that, our, how do I say this? So we kind of like add some noise to this shit. To like positions. Because, okay, so we can change, we can fix this. Let me find the randomization parameters for a second. Can we... Where is like our size here? Just for a second, let's generate bigger ones, just so we can kind of like show what I'm trying to talk about. Why did that start causing problems? Not liking this. That shouldn't matter. So changing the size is fucking shit up. That's interesting. That's surprising. Is there like a 256 hard-coded somewhere? No. That's not good. Oh, right. Our backgrounds have a hard-coded size right now. Ah, fuck. That's annoying. Okay, well, we can still show this by increasing, we can leave these things at 256 by 256, but increase the size of the barcode in the image for a second. That should help visualize what I'm trying to show. Hold on. We can get there, we can get there, we can get there. Hold on. If we just take the scale here and make it 1.0. Okay, so we add some noise to the like coordinates of the barcode as we sample from the code because we want some sort of distortion on here to kind of match like in real life sometimes the barcodes are not like straight, right? That's kind of like the intent here. And by doing that, the edges of the barcode are probably moving relative to what we think our width and height are because we're like applying noise to that thing, right? So we should be able to be like, if I set these noise multiplier range to 0 kind of for a second, that should make it so that the bars are always straight and that this no longer happens, right? So now what we should see is that the our boxes like perfectly match, right? Which I think we are seeing now, which is great. So that means the question be like, for now, maybe we kind of put a pin in this and say, look, we need to bring this stuff back, but maybe we like weight the distortion so that the edges stay straight, or maybe we allow like less distortion at the edges, but still allow some. Maybe we just let the boxes be wrong, but I don't really know like how I want to handle that right now. So I think what we'll do is we will try to train something now that just doesn't work for the like wiggly stuff, right? And we'll come back to this later. Okay, so somebody put up a good point that I should be square rooting the width and height in the OpenCL outputs here, because that's what we're going to be feeding to our comparison, our like loss function later. So let's do this. And I guess this is represented as offset from the center, so that's all chill as well. And then here, just in our visualization stuff, we should be squaring the width. And we'll just put here, note width and height are square root as inspired by YOLO V1 paper. So this should still work, and it should just be like the numbers are a little nicer now. Okay, chillin'. So that's kind of like this done. Kind of this is ready. And I guess now we want to hook this up to our training loop. So let's kind of take this visualization stuff that we just did. We need to like pull this out into somewhere that can be used on the training side as well, not just like the data generation visualization side. So let's put this in like training sample view and just kind of make a function here that's like, surely this can all be like squished into a function that's like generate OpenGL buffer. We have one already actually for orientation. Make orientation buffer. So we can call this make bbox gl buffer or something. And this will return some like render source that we can throw around. Cool. He's gonna want some stuff, right? So we're gonna do like bounding boxes here is going to be some sort of like tensor. Okay. So that kind of gets this out of here. We have selected image. How do we do this for make orientation buffer? We gave him the orientation directly. So we can kind of maybe make this a CPU tensor. Hello? Oh, it's like it's actually like a math tensor that is backed by a floating point array, I think is how we usually do this. Which kind of takes this stuff out of it. And then we call this everywhere. I guess this is bounding box. And everywhere we see res in here, res.val turns into box. Cool. We need a GL allocator where this stuff is going to live. Where does this stuff go so that I don't have to worry about freeing them? And so it's like everywhere that says self scratch GL gets GL alloc. Cool. Then we need the program that this is going to be rendered with. So we'll say he's going to be this guy. Okay, and then we don't do the render here. This comes back out because that's kind of like an external thing. So here now, all of this is like render source is, oh wait, not all of it, all of this stuff. Make bbox gl buffer. And this is like, give me scratch GL. What else does he want? He wants the box. Interesting. That's interesting. I guess the type here is not what I thought it was. This is just a bunch of floating point 32s, I guess. Okay. Then this guy gets program as well. All right. And then this guy is mad about something. Surely this can fail, no? Yeah. And then we have to return the render source. Of course. All right, are we chilling? So this stuff still works, great. And so now we can take this function and put it in the training stuff. So this guy, architecture of our neural network training is that like GUI's in one thread, training's in another. So the train thread is responsible for generating data. And so part of what he is going to do is he is going to tell the GUI thread his like expected results. And so I guess this generate training input guy, he used to say, our expected value was a mask, right? Which is no longer true, right? Our expected value is now just, it's literally just like bars dot bounding boxes, right? That's all we're trying to predict right now. Eventually, we're gonna have to like coalesce multiple pieces of information into like one thing, but for now, this is great. So we are trying to predict bounding boxes now, which means that we don't need to reshape the masks anymore. Ooh, do we need to reshape the bounding boxes? We might. No, we can just make them number of images by stuff. That's fine. That should work for us. Now, if we were trying to run this right now, shit would like fall the fuck over. He's gonna be like, yo, what the fuck? Like, the things you're predicting aren't the right fucking shape, right? So let's try to figure that out for a second. So this is kind of part of our layers here. So our final output, they said linear output. We're going to want to output something that is 5 outputs just in general, right? It's like fucking give us our bounding box. Take all of the information that you have, make some bounding boxes. We might need multiple layers, but this is fine for now. We'll kind of figure that out. And then we will reshape that thing at the end to 5 boxes by number, 5 things by number of images. That's great. Okay. So now does this like run at least? Yes. Now we are trying to visualize the bounding boxes as masks, which is bad. So we're gonna have to figure this out. But what I'm really interested in for a second is just to see, does it look like this loss number is like decreasing? It's hard to tell. Hard to tell. So I think that what we want to do here is start visualizing the predicted boxes. Oh, it looks like it's not. It looks like it like might actually be growing. So it's possible that we don't like have enough network capacity to like learn this stuff. But let's just start by trying to like pipe the data of this stuff back over to the other side and like visualize it in a sane way. So, oh, we're using the wrong loss function. We were supposed to do like squared error here. And we're also looking at the wrong layer output, so that for this as well, which is like another obvious problem. So can we look at, yeah, -1. I'm surprised that that was even working, to be honest. That feels like that should have been crashing. Okay, so now we're seeing this stuff go. He's at like 300, 245. Let's decrease linear a little bit. 240. So it doesn't, I'm not really convinced this is learning, but it'd be interesting to learn what it's doing, right? Because you can see here for sure, just based off like the striping on this image, you can tell that the left two, the offset from the center, these guys are staying like relatively close to 0. Then like the width and the height are like not 0, and the rotation seems to be like kind of fucking random, right? So there is like something here, but it might not be learning enough, or maybe what it's learned is already good enough, right? Those are our options. So let's try to visualize this stuff a little bit more sanely. So it looks to me like all the data that we need is already over here somewhere. And so what we just want is some way to like add a bounding box prediction, or like render bbox overlay or something. So this guy is going to take in some stuff, and he's going to call that function that we had, right? It was like make bounding box GL buffer. So he takes in our GL allocator. He has the box, which should just be overlay buff. Yeah, should be. We should have a program we're trying to render with. We might not have the program that we need right now. The OpenGL program of solid color program. We do. Solid color renderer. We don't do anything with this guy though. So we need to save this here maybe for now. Sure. And this will allow us to render some shit now. So here we should be able to go like self widgets, solid color renderer, hype. Looks like this scratch CPU scratch allocator is not needed. We make a render context to like do stuff. And I guess this goes down here after the checkpoint of the allocator. And here we go, like bbox, bbox source. And then we call self widgets, solid color renderer, render line loop with the bbox source. And here we have transform is, what was it? Is like stud math transform inner identity inner like this. And then it was color is let's do blue. All right, let's see where that takes us. So here we should be able to be like render bbox overlay with the expected. And maybe we will also render actual. Why not? So this is expected. This is what we predicted. Okay. Let's see if we should see two boxes now. He's annoyed at something's bad that we didn't like pass some parameter around. Solid color renderer. Boom. Easy. All right. Let's see. Okay. So we should distinguish between the actual and predicted, right? Obviously. Obviously. So can we set the color here? I don't know. Here, we'll just kind of do this. All right. Okay, so red is expected, blue is predicted, and then we need to make sure that blue is coming on top, which it is. Okay, cool. Cool. So we can let this train for a little bit, and we can kind of like start trying to look at this and inferring what it's not doing right. So it looks like orientation is not learning. What I would love to see actually for a second is like, can we weight the loss function so that it only tries to learn one of these things for a second? Oh, because it's hard to know like what's happening, right? I guess we could check the gradients for like okay, this is concerning, right? This is concerning. If we look at the gradients, we have not very strong gradients at all. Okay. We could what else do I want to do maybe? Can we look at oh, interesting. Okay. So we can see at the very least, is the center starting to line up? I think I might be seeing it starting to kind of move around with it. Not entirely, but there are cases where it's like starting to jump over. Okay, I also want to let's take the backgrounds out of this thing. Oh, we also need to fix the noise shit here so that they're always square. And then I want to see what happens if we don't do sampling from like good images. If we just like make the background really simple so that it's easy for it to figure out, that should make our lives a little bit easier. So we should be able to go here, and I think we have a randomized color as part of our parameters here, if I remember correctly. So let's just do that. Okay, so the question is does this learn faster? So you can see, like, to me, it looks like it's trying to do something. It's not learning width and height very well yet. You could argue that, like, the rotated width and height are, like, confusing signal to it. But you can definitely see he's starting to, like, follow the box around, which is good. So we're getting somewhere. For sure. We need some sort of metric to see if we're converging or not. Yeah, true. Like box crossing, space crossed. I mean, really, loss should be that answer for us, right? Like this number decreasing at the top. He's like, with this simpler problem, he's definitely getting closer, right? This like 75 with like, it was getting stuck at like 200 before. So you could kind of argue that like network capacity wasn't strong enough to do it before. Where here we're definitely starting to see something start to happen. He might need a little more time. But yeah, we're starting to see something. So the question is where do we go from here? Maybe give it more brain cells. Yeah, that's definitely an option for sure. I think that when we were doing rotation prediction initially, we found that we wanted a few like linear layers at the end, right? Because our initial thought was if I have a bunch of bars going across the screen, I want to know. You could do this in like a couple steps, right? You could do a horizontal edge detection and vertical edge detection, and then you could get like the orientation by just kind of like normalizing these vectors, right? So we kind of reasoned that you need to be able to approximate adding these things, like adding a squared plus b squared and then square rooting them so that you could get like your Pythagoras, right? C is equal to a squared plus b squared equals c squared type shit. So we just added a few linear layers at the end. You could argue something similar here where once we have like the rotate, like our convolutions are not doing a lot of the like heavy lifting. They're kind of like pre-processing the image. And so we need like a few linear layers to like do a little bit of like shenanigans to like pull out the information that we want. Right? That's kind of like an argument that we could easily make. And so here, what we should do is maybe throw a couple linear layers with ReLUs here. And we'll start, instead of going directly to 5 outputs, maybe we go, oh, sorry, ReLU, we need to look at this. And so let's kind of like just like work our way down. So like maybe we'll go to like 64 things, and then we'll go from, 64 to 32, and then like 32 to 16, and then like from 16 to 5 or something. Just give it like some space to like do some complex work at the end. And let's see if that like improves our results at all. This is concerning. This seems bad. Is our initialization wrong? Might be. I also want to try maybe huck some sigmoids in here just to see if that changes anything. Because I know that's what we did last time. You left a ReLU after last layer, did I? That's also a really good point. Thank you. That's pretty fucking bad. Good eye, good eye. Okay. So what I guess like what we should do is we should start like thinking about like convergence time. Right? So do we think that we're getting stronger within a certain time frame is like a question we should be asking ourselves. But like, okay, we have a number here, 50. I think before this change, I think 50, 40 was like where we hit our limit. So I guess if we just leave this for a little bit and we start seeing this number drop to like 30, I saw a 30 in there. Let's also like drop the learning rate a little bit. 0.8 feels, or 0.08 feels high. Yeah, interesting. It's definitely getting somewhere. It's not good. 25. We should also be, what we need here is we need like time in here. This log needs to get better. But, okay, let's leave it for a little bit, just a little bit longer. Let's take out the stopwatch. And we'll give ourselves a limit on how long we're willing to watch this thing for. Like, let's say we'll leave it for 1 more minute. And once we get to 1 more minute, we'll see if we feel like it's okay or not. Definitely, like, I feel like these numbers up here have definitely decreased, right? Like, 20, I don't think that we were seeing that before. We could also argue maybe we should drop the learning rate a little bit, but we'll see. And then once we get to a minute, we can kind of compare many images and stuff. I mean, definitely something's happening. This is exciting. I suspect that we are going to find out that we might need to, like, what are our options here? Network capacity, it literally can't learn enough with the current form, right? It's just not, it just doesn't have enough information. Another option is that our training target is not very good, right? I wouldn't be surprised if we should be weighting the center for our loss a lot higher, right? Like, oh, sorry, let's pause this. Right, like, the center of this thing should be, like, if the width and height are a little bit off, that's not a problem. Things that we care about, right? In terms of, like, barcode scanning, rotation and center are much more important than width and height. Well, width we could allow overestimate, right? So we could punish width harder for being too large versus, or sorry, too small versus too large. And then height, we probably don't care about nearly as much. But, I mean, this is definitely something, right? It's definitely something. We can see that it's, like, definitely trying to follow this stuff around. So I think the next steps here are, like, just kind of, like, more experiments, unfortunately, right? So I think, unfortunately, the nature of this, like, AI stuff is that you kind of need, like, time for experiments to run. And I think a lot of the development is kind of, like, setting up the types of experiments you'll want to run. So I think that we've got some relatively good proof that we have a training target that is working, right? Now, network is not learning the things that we want it to learn quite well enough, but I think that this probably means that I need to do some, like, overnight offline kind of, like, let the GPU run and try a few things in the background. Maybe we'll find out that it just needs to train for longer. Maybe we'll find out that we need more capacity. Maybe we'll find out that we need to adjust the training targets. But all of those are kind of like little fiddles over what we're doing. So I think what I'll do is I'll train some stuff overnight, see kind of what comes out of that. And depending on, like, what I see, probably the plan for what we do next will be different, right? Maybe if we find out that it's just fine after a longer training, then the next thing to do would be, like, checkpointing, right? So that we can have something to work with. Maybe if we find out that the problem is that no matter what, no matter how big I make the network, it's always shit, then, like, we're gonna have to, like, adjust the training target and see if we can, like, get some inspiration from, like, YOLO version 2 or something for how to, like, predict these things better, right? There's all sorts of options here. But at the very least, our boxes need to get better, but also at the very least, we have something that does something. So that's exciting. So I think I'll call it there for today. Thanks for watching, guys. I hope this is fun for you. If you like what you saw, we stream most days. We aim for 12:30 Pacific time to 4 o'clock Pacific time, you know, so it's 3 Pacific time now. So anywhere between 2.5 hours ago and an hour from now is when you should expect to see us live. We're working on this neural network training framework right now. But there's a lot of other stuff on the YouTube if you want to check that out. We tried to make an Xbox controller with, like, an operating system, terminal emulator, like a Google Maps replacement. There's lots of, like, stuff in there. So if you want to check that out, there's a link. If you're watching on the YouTube and you want to swing by and catch us live, there's a Twitch link in the YouTube description. Some stuff from stream goes up on the YouTube, some stuff does not. It basically depends on the feature development typically goes up, but you know, there's just too much stream to post, I think. So the rest of the stuff gets, you know, maybe like reading or unit testing or cleanup, you know, that type of stuff. That stuff gets posted on Patreon, YouTube members, or you can see the Twitch VODs if you pay in the appropriate place. We do that so that we can give something back to people who want to support the stream. You get the knowledge that you're helping the stream continue, because when I run out of money, I will have to get a job. So every dollar I make does extend the life of the stream by some amount. Anyways, I think that's it. YouTube, peace out, and Twitch, let's find someone to raid.